So let's now try to derive what are called order conditions for a second order explicit Runge-Kutta method. Okay, so and to make this more precise, I'm going to set the number of stages as to 2. Okay, so that means that the general form of an explicit two-stage Runge-Kutta method is the following: that y1 is equal to yn, right? y2 is yn plus h times basically a 2-1 f evaluated at y1 tn. Okay, and then finally it's like yn plus 1 is equal to yn plus h times v1 f evaluated at y1 tn plus h times v2 f evaluated at y2 tn plus c2 times h. Okay. All right. So this is the general form, if you will, of a two-stage explicit Runge-Kutta method. Again, the idea it's like behind explicit methods is that you can write down the equations in such a way that you never have to solve some sort of implicit equation in order to compute the things you need. So y1 is just given in terms of yn, which is given to you. y2 is in terms of yn and y1, which you've computed before. And then yn plus 1 is expressed in terms of yn, y1, and y2, which again you've computed before. Okay, so so nowhere it's like in this process do you have to solve some sort of nonlinear equation in order to compute the things on the left-hand side. Okay, so so what you can do then is if you look at this expression, this is what you actually are looking for at the end of the day. You want this to be a good approximation of y at tn plus h, basically. And so the way we're going to approach this is that we're going to essentially do a Taylor expansion about y n tn, right? So we're going to Taylor expand about basically the point yn tn. And in particular, it's like we're going to look at this last term first. Okay, so let's look at f at y2 tn plus c2h. Okay, so I'm going to substitute the expression for y2. So this is f evaluated at yn plus h a21 f at yn tn, comma tn plus c2h, and I'm going to expand this. It's like about the point yn tn. Okay, so so this is equal to f at yn tn as the leading order, the zeroth order term in the Taylor expansion, and then the next higher order, which involves a first power of h, is the one which involves the partial derivative of f with respect to y, right? So there's a df dy evaluated at, again, yn tn. And then you have to multiply this, if you will. It's like by the step you've moved, right? There's already a factor of h out there. I'm going to put the remaining term here, which is a21 f at yn tn. Okay, and then there's a derivative with respect to time plus a df dt term, again evaluated at yn tn, and then the shift is C2 times H, but I've already taken the H out, so it's just C2. All right, so that's the expansion to sort of something which is of order H squared, right? So I've looked at the linear term, and so I can then have an error term of order H squared. Okay, so now I can take this and I can substitute it into this expression for yn plus 1. Okay, so I get yn plus 1 is equal to yn plus h times b1 f evaluated at y1, which is just yn. So I'm just going to put yn tn, so I don't really have to do anything about this because it's already evaluated at point yn tn where I'm doing the Taylor expansion about. Okay, and then the next order term is this piece here. So again, there's a factor of h, right? Plus h times f at yn tn. Sorry, there's a b2 as well. Okay, plus h times df dy. So I'm going to omit the where I'm evaluating them. Again, the idea is that they're just being evaluated at y and tn if I don't explicitly state this. So there's an a21 here, and then there's an f, right? Plus there's a c2 df dt term. Okay. And then now the error I'm making is something of big O of order h cubed, because this f term, it's like it's being multiplied by a prefactor of h. So the error which I've made, it's like in truncating this Taylor expansion, just gives me something of order h cubed. Okay, so this is yn plus h times b1 plus b2, right, f. Okay, and again, I've omitted the yn tn term. All right, plus now as a h squared b2 term multiplied into a 2,1 df dy times f, right, plus c2 df dt, again, plus something which is big O of order h cubed. Okay, so so this is more or less a Taylor expansion of the numerical solution you get from this general form of an explicit two-stage Runge-Kutta method. So what you want to do now is you want to compare this with the corresponding Taylor expansion for the solution. So let's see what happens when you do that. Okay, so you know that y at tn plus h, right, can be written as a Taylor expansion, which is about tn now, so that's y at tn, and then usually it's like you identify this with yn, okay, plus, and then plus h times y prime at tn plus h squared over 2 y double prime at tn plus something which is big O of h cubed. All right, so so I'm only interested, if you will, in matching the Taylor series up to the second order in h terms, leading a error term which is big O of h cubed. And as you recall, when you have a you know, it's like when you have a local error of big O of h to the p plus 1, then your method is order p. Okay, so if you match everything up to second order, and then you have an error term which is big O of h cubed, then the order of the method you get is order 2. Okay, so so let's see what happens here. All right, so the problem, of course, is that y is a solution of a differential equation. You don't have an explicit formula for y. And all you really have is the differential equation. So you have to replace these terms, it's like with the corresponding terms coming from the differential equation. So you know that y prime is f of y and t. Okay, so I can replace this term here with f at basically yn tn, which is exactly what I want. But then I have to deal with this y double prime term. So y double prime, of course, is nothing more than the total time derivative of y prime. Okay, so that is equal to this partial derivative with respect to t plus f d dy applied to f of y and t. Okay, and that's because this term here really is dy dt d dy. Okay, so this is part of the expression you get. It's like when you're doing this total time derivative. Okay, so in any case, what you get is df dy, df dt plus f times df dy. Okay, so that's the next order term. So this term here is df dt plus f df dy. All right, and that's all right, because if you look at what we have here, we have terms involving f, we have terms involving f df dy and df dt, right? So all these things show up in this Taylor approximation. Okay, so maybe it's like I will write this out more clearly. So this thing here is equal to yn plus hf, and I'm going to drop again the yn tn terms, right, plus h squared over 2, right, df dt plus f df dy, plus an error, which is big O, of h cubed. Okay, so now I'm in a stage where I can compare the Taylor expansion of the exact solution with the Taylor expansion of the numerical approximation, which comes from the explicit two-stage Runge-Kutta method. Okay, so in particular, if you want this thing to be second order accurate, which is to say that the mismatch between these two things only occurs at order h cubed, then you have to equate essentially the coefficients of these f's, df, dt's, and so on. So you want this to be true for any possible f, and so in general, it's like what you will want is, or what you expect, is that the f's will be, in some sense, independent of the df, dt's, and the df, dy. So you just basically match the coefficients, it's like of all these distinct terms involving f's and their partial derivatives. Okay, so there's an f term, it's like of order h, that obviously corresponds to this hf term. So what you need is that, so the conditions, if you have for second order, are the following, that you have b1 plus b2, right, has to equal to 1, right? That's what you get by matching the term involving f times h, all right? So this comes from the h times f term, if you will. All right, then you also have another condition, which comes from matching the h squared df dy times f term. So there's comes from the h squared df dy times f term. Okay, and so on the numerical method, it is as a b2 a2-1 coefficient. And from the Taylor expansion, we see that it has a 1/2 coefficient. Okay. Okay, and then the third condition, if you will, is the third condition, if you will, has to do with the h squared df dt term. Okay, and there's a b2 c2 term here, right? That's a b2 c2 term. That is also equal to 1/2. Okay. So, all right. So what does that tell you? So there's a b1 plus b2 is equal to 1. There is a b2c2 is equal to half. There's also a b2a21 is equal to half. So these two equations together implies that the last two equations implies that c2 is a21. Okay. So the point is that these are what are called the order conditions. That these are the conditions. It's like on the coefficients of the Runge-Kutta method, the AIJs, the BIs, and the CIs, which guarantee that the method is at least second order accurate, right? So nothing in this analysis is like proves that the method is at most second order accurate because we haven't really taken the expansion up to higher order, but by satisfying these order conditions, we guarantee that the method is at least second order accurate. Okay. So let me just erase some of this and then rewrite those order conditions down. Okay. So there's an order condition that says that b1 plus b2 is equal to 1. There's an order condition which says that b2 c2 is equal to 1/2, and there's an order condition, so these two imply that c2 is equal to a21. So let's write it as c2 is equal to a21. Okay. All right. The number of active unknowns, if you will, it's like in the method, aren't that many. Okay, so because essentially we have an unknown a21, we in principle have an unknown b1 and b2, and then there's an unknown c2, right? So there are 4 unknowns, okay, but only 3 equations which constrain them. Okay, so what that's telling you is that explicit second order two-stage Runge-Kutta methods, right, are not unique in some sense. There's more than one of them, potentially. Okay? So again, these conditions do not uniquely sort of specify a two-stage explicit RK method. And it turns out that there are many examples of them. So there are many examples. From this, it's like you might suspect that there is a sort of a one-parameter family, all right? Because you can write everything. It's like in terms of just specifying, for example, b1, right? So if you specify b1, you know what b2 is from this first equation. If you know b2, you can know what c2 is, and again, if you know c2, you know what a21 is. So it's easy to see, right? These are parametrized by the choice of basically b1, right? And then b1 can be anything in the reals, right? So if you choose b1, then b2 is equal to 1 minus b1, right? And then from that, you know that c2 is equal to 1 over 2 times b2, which is 1 minus b1. So I'm just going to write everything in terms of 1 minus b1, just be very clear. And then this is, of course, equal to a21, right? So if you know b1, it's like then everything else is specified. So from here, I guess it's like you don't want b1 to be 1, but you know, modulo that, it's like you're okay. Okay. All right. So there are many choices. It's like and you can write down. It's like a Runge-Kutta method. It's like you know, the A's, B's, and C's. You can write them in the form of what is known as a butcher tableau. Okay. So you write this as the form, this A matrix, C vector, and then this B row vector is written as a row vector. Okay, so we'll go back to discussing butcher tableaus. It's like you know, how you can transcribe its like Runge-Kutta methods into this form and go back and forth between them later on. But for now, it's like, let me just throw this out there, and then it's like looking at two-stage explicit Runge-Kutta methods, which are second-order accurate. Then there's a sort of a parametrized family. It's like of them, and then I'll give you some examples of this. So so you have something which looks like this, right? So you have a method which looks like this. You have a method which looks like 0, 2/3, 2/3, 1/4, 3/4. Then you have a method which looks like 1/2, 1/2, 0, 1, 1. Okay. Okay. So anyway, so these are sort of just some examples, if you will, of very commonly used two-stage explicit second-order accurate Runge-Kutta methods. So in principle, it's like one could push the analysis further. It's like and look at sort of third-order schemes, and so we'll look at that in a little bit. Okay.